welcome to our first session for this year. We're opening with Tom Pratt, who is already an adjunct at DCCC, mathematics. The title of his talk is Rocket Scientist. What rocket science, I have no clue. I'm a biologist, so I asked him, earlier to tell me something about UFOs. He pretends that he doesn't understand, he doesn't know. He wants to talk about earthy things. Nevertheless, Tom has graduated, he has received his PhD at Applied Mathematics at Rensselaer Polytechnic Institute in New York, and he has extensive experience, both academic and industry. He worked as tutor, lots of teaching, as an adjunct in many different institutions. He has series of publications, research publications. He has worked mainly with Lockheed Martin, as well as other corporations, United Technologies. I think that I will stop here. He's the expert to go in detail and tell us all what a crazy rocket scientist does. Okay?
Thank you, Elias, for taking care of this speaker series. Also thank to Dean Rodrigo Carmignana for interviewing me and suggesting this might be a good topic for today. Very thankful for that. I'm excited to be in the STEM speaker series. This talk I'm giving today actually started in the Radnor School District where we live, and we've been giving it several years to high school and college, middle school children. So now it's morphed into a college level presentation, which I'm going to go over today. It's been said. Mike, is this mic working? Everybody hear me fine?
Yeah.
Okay. It's been said that everyone has three careers, and in my own case, it's certainly true. I spent my first career. I got out of grad school, and I wound up in Connecticut working for United Technologies Corporation, which is a big conglomerate, and they own Pratt Whitney aircraft, which makes jet engines for the free world, and also for the military. So I spent pretty much half a career there. Then I got homesick. I was born in Philly and down in this area. I had an opportunity to come back and work for Lockheed Martin. So I took advantage of that to work for their space program over here in King of Prussia Valley Forge. But of course, as you know, we have offices all over California, Colorado, Texas. I mean, I've traveled extensively for them. It's a very exciting career. Now, my third career actually started yesterday. I taught my first class on campus here as an adjunct faculty member of the math department. So I'm looking forward to my third career right now. Rocket scientist. Every time people say, what did you do? I said, well, I'm a retired rocket scientist. And everybody laughs. And it's kind of a common reaction. Everybody thinks, well, you worked at Wall Street or you're a financial whiz kid or something. But actually, there are people that did work in this area in rockets and satellite technology. So I'd like to give you an overview, first of all, of the entire aerospace industry. Spent a couple slides here. The big names in commercial industry are Boeing and Airbus. Anyone's ever flown, or anyone's flown recently, has probably been on one of those airplanes. They by far have the most. And then a long time ago, the government said, well, you can't make the airplane and the engine. It has to be two separate entities. So the GE and United Technologies, where I worked, make the engines for those airplanes. And the third player is Rolls-Royce over in England. Surprisingly enough, everybody knows them for automobiles, but they also make jet engines. They're very good at it. Honeywell also makes climate systems, things that go inside the aircraft. Defense industry, Lockheed Martin is renowned to be the largest in the world. And again, almost 48 states have Lockheed Martin facilities. I worked there. Raytheon, General Dynamics, Northrop Grumman, these are all, and you notice there's a lot of conglomeration, like Northrop merged with Grumman, Lockheed Martin merged with Martin Marietta. There is in fact an alliance between Lockheed and Boeing to make rockets. The government was saying, oh, you have one, next year you'll have one. They said, why don't we combine them, make it the United Loss Alliance. For government, NASA has been the prime driver for the early space program. Navy, Marines, Air Force, and maybe the Space Force are also people we sell to, part of the industry. And what I find interesting now are this, in the last 15 years, commercial entrepreneurs have really changed the face of this industry. A lot of these are billionaires, right off as Elon Musk. Perhaps you've ridden in a Tesla or have a Tesla. He made that. He made his money in PlayPal. He made $1 billion, but it turned out his real dream is to go into space. And so he set up SpaceX, or space exploration. And he's now taking a lot of business away from Lockheed and Boeing. His friend, Jeff Bezos, is vowed to be the richest man in the world. He started a small company called Amazon, which mushroomed and is now taking over everything. It turns out he also had a hidden dream. He'd really rather be delivering packages with drones. He also has this little startup called Blue Origin, which is now making rockets for the space program. Richard Branson, kind of a generation ago, he had Virgin Airways to go from England to here. Now he's morphing it into Virgin Galactica. He wants to take people into space for a fee. Smaller startups, Digital Globe, Orbital Science, and so on. Interesting one is analytical graphics. You notice they're next to DA. If you ever see any TV shows with computer graphics or in movies, a lot of times you have simulations. It's made by these guys. They're actually people that left the group that I was in at Lockheed. They went for their own company. They've been voted the #1 place to work 2 years in a row. Not this past year, but recently. You go out to their campuses like California. Everything's open, free food, daycare. It's a really exciting company. The overall industry, $870 billion a year. That's impressive, but what I find more impressive is the fact that $90 billion a year go to offset our trade deficit. Everybody's concerned about that. We import everything. We import automobiles, smartphones, televisions, clothing. We actually provide a positive surplus. I think American movies are also part of that. I believe we export them also around the world. And as you can see, it's a great home for STEM employees. For today's talk, I thought I'd look over some of the fields of study that are relevant. In science, it's all the classics: physics, chemistry, biology, medicine, astronomy, and metallurgy. You'll see how important that is. Technology, CAD/CAM, this is computer-aided design and manufacture. Heat transfer, sales and marketing, cybersecurity. When I left Lockheed several years ago, everybody was going into cybersecurity because all the threats to our infrastructure and our web services. Art. Think about it. A lot of times the initial concepts are in design and modeling phases. So what better to do that than an art team? Audiovisual are very important in not only selling products, but also demonstrating how they'll work, how we're going to get to Mars, and so on. And advertising, to stay in business. Engineering, all the classics: mechanical, aeronautical, electrical, chemical, industrial. And in math, software development. A lot of mathematicians are coming in, and the best home for them is the software development. But in the old days, that used to mean, well, you're going to be writing code, you're going to be learning, you're going to be using Python or C++ or something. But now, it's a lot of, there's a marriage between people who do algorithms and people who can actually write the code. It's no longer separate. And so that's taken on a whole new meaning. Algorithms are pretty much what I did. Operations research, finance, cryptography, and numerical analysis. The nice thing is that there's a lot of synergy. It works, you may not know, actually when I joined Pratt Whitney, I didn't know anything about aerospace. I was pretty much a theoretician in graduate school. But by working with all kinds of people with different backgrounds, you have on-the-job training. The group I just left at Lockheed, my boss was an award-winning science fiction writer. He actually won national awards. A coworker in my group was on the Quark Discovery team, University of Chicago. And when that project went down, he said he wanted to go into aerospace. So you never know whom you're going to run into. There are many, a lot of give and take. Problem-solving skills, as you'll find out, are very important and revered. Okay, so let me start with the beginning of my career. Out of grad school on the Connecticut. Pratt Whitney Aircraft had a ring to my name. I said, geez, I'm going to work for Pratt Whitney. Unfortunately, I'm not related, but it was a good place. I got a lot of respect when I traveled. Okay, here are some of our projects. 20,000 jets worldwide. Boeing 737 is the most common in the world right now. With its range of over 4,000 miles, it can go anywhere. It's very, very safe. I mean, it's having millions and millions of in-flight hours. 200 passengers. All these planes fly in the 500 to 600 mile range. The Dreamliner is the one that they're hoping is going to take a lot of business away. Double the range, 330 passengers, much more comfortable. Again, twin engine. That's the key thing. The original workhorse was a 747, but that had 4 engines. So to get flight safety with 2 engines was key. The Airbus 380, I'll mention this. This is the largest plane ever, commercial plane ever used in service. It's too big for Philadelphia. They said if it came in here, it would knock down the light poles because the wingspan is so great. And so it only can land in like New York City, I think Dallas, probably Washington, probably Dulles. 555 passengers. I mean, that's even more than the 747 and the largest ever. Now note that its sister ship, the A350, just announced last week they're going to have the longest flight on record. It's going to be 11,000 miles, New York to Singapore. It goes over the North Pole. I think it takes 19 hours, so that'll be a lot of fun. If you like that kind of thing. I freak out when I go over Greenland and I'm looking down at icebergs and it's just, and they say, oh my gosh, I made these engines. I hope they're going to survive this trip. Okay, military aircraft. We had Pratt Whitney South and West Palm Beach worked on engines for these aircraft. Joint Strike Fighter is purported to be the last manned strike fighter. From now on, they think after this it'll be all drones and robot control. This is an exciting plane. It has great stats, good range, top speed, not quite Mach 2. Supersonic cruise means in the old days you needed turbo, what do you call it? Anyway, you needed extra power to get to supersonic. This one, you can cruise the supersonic with this engine. The vertical takeoff and landing, everybody knows about that. It can do that from an airstrip. It's stealth. But it's a marriage of the F-16 Falcon, which has great flight characteristics in a dogfight, but it's not stealth. This plane has those characteristics on stealth, which means it's the size of a sparrow on a radar screen. Blackbird is one of my favorite planes of all time. It's something out of science fiction. In the Cold War, in the 60s and 70s, huge range. You could fly over the Soviet Union. At that speed and at that altitude, you couldn't be detected, couldn't be shot down. One thing I was always wondering, why is it black? Most aircraft, are silver or white. And so I asked the pilot. We had a pilot speak to us one day. I said, "Why is it painted black?" He said, "Well, at this speed and in this altitude, there's still so much friction that these engines glow almost to the point where they're transparent. You can actually see the turbines and the fans turning in here. And so there's excessive heat. The best way to get rid of heat is to have black body radiation. It's more efficient than any other color. So it's actually a way to shed the heat at those speeds. B-2 bomber looks like this, kind of like a flying pancake, flying wing. It's very scary though. It's subsonic, but it's stealth. And its mission is to go in after, if there's a nuclear exchange, it can go in after and do its business without being challenged. By the way, if you have any questions, feel free to pop up. I mean, anytime. Oh, here's the vertical takeoff capability. The pilot, this is the F-35. The pilot sits here, and then there's a fan right behind him or her. And what happens is the fan has downward thrust here, and it's also coming out of the wing. So you have these three columns of air, and then the rear of the engine, it's called vector thrust. It actually rotates down, and you get a fourth column of air. So it's very stable when it's coming up out of a landing site in some denied region or off of an aircraft carrier or wherever it is. So that won the Colley Award, which is a big engineering accolade. The engine I worked on, this is a cutaway engine. It's called a turbofan because it has a turbine here, has a big fan here. One of the most complex machines ever built, supposedly. My building had over 4,000 engineers in it. And they were all groups. There was a turbine group and the compressor group and the airfoil group. So basically air comes in here. It's brought in by this rotating fan. It goes through, this is a compressor, which, its job is to compress the air, maybe 20-to-1 ratio. And then here's even a higher compressor. Then when it's, at this point, fuel is injected, jet fuel is injected, so the exploding gases then go out the rear end and rotate the turbine. So this is called the hot section, and then the faster this goes, the faster the fan and this turbine are on the same spool. So as the turbine goes, that drives the fan. So that's basically how it goes. A lot of the air goes over the engine. That's called bypass. So it's like a propeller that, and that's where you get a lot of your thrust from. Now, my very first day on the job at Pratt Whitney, we had a small group, like four of us, four mathematicians, and my boss said, well, you've come in with some background in differential equations. We looked at your thesis work and so on. And we have a problem these days called foreign object damage. When birds hit the engine, there can be problems. I mean, it's expected. A lot of birds live near airports, which are near swamps. And if you remember the movie Sully a few years ago, he was the unfortunate pilot of a 730 of a plane that hit two flocks of birds. So he didn't lose just one; he lost both engines, and he had the dead stick land in the middle of the Hudson River. So he's a huge hero, saved everyone's life. And this is what this thing can look like with this bird damage. You can take off the nose cone, the surrounding the cell. So, going back to my undergraduate days and my grad school days, I said, well, this is really a vibration problem. Now, many of you, if you may not have seen this equation. This is a differential equation. It models this system. This is like your car. If you have a mass here and a spring, this will bounce up and down. You have a shock absorber here to slow it down. So this is called a spring mass damper system. And the equation, mathematical equation, is this. It's a differential equation, which is no more than it's an equation containing derivatives. So you have y, which is the location of this mass, and then you have y prime, which is the velocity, y double prime, which is the acceleration of that mass. So that's a nice linear equation. And I actually put in some numbers here. Okay, here's one with actual numbers and actual initial position, initial velocity. There's a solution. So everyone's seen this. It's e to the minus t times the sine of t. So the sine of t is an oscillatory response, which is what happens. If a bird strikes and you lose a fan blade, there's going to be vibration. So there's going to be sinusoidal response. And what you like to see is decaying over time. And that's what E to the minus t does. It decays it over time. And so that's what you want to see. In the real world, this is what we actually worked on. This is a model of the entire engine. There's the compressor, the turbines. There are spring mass systems all over the place. We had 292 lump masses. And so the idea is if something goes wrong here, what's the response down here? And so look at that. The equation's the same, except that instead of having scalars here, you have matrices. And instead of y being a single location, y is a vector of locations all throughout the engine. So it was amazing to me that the work that we actually did in graduate school could be applied to something as wonderful as this engine. And so we could then predict, well, what happens if a bird hits the engine, the blade comes off? How's the engine going to respond? Sometimes the bird hits here, and the tail cone falls off. There's kind of a teeter-totter reaction. So we're trying to predict that. But the proof's in the pudding. No matter how good our analysis was, you always have to go with an actual engine. So here's what we call a test rig. And we take blade 1, which is here. We put an explosive charge at the bottom here. And when it hits top dead center, you set off the charge. The blade is released at 4,000 RPM. It's got the kinetic energy of a Cadillac hitting a brick wall at 50 miles an hour. And the idea is what happens to the other blades? Do they notch? Do they break off? Does this nacelle contain the debris? So we have to pass that test for the FAA, otherwise you can't fly. The other thing is we have another test. We have a cannon that shoots dead birds into a rotating engine. That's to simulate what happens in flight. And again, you have to survive that and shut down. Don't want to dwell on this, but this was in the news last spring. You probably see this. It was a huge event for Philadelphia. In-flight emergency. They lost a fan blade, not on takeoff, but at 32,000 feet. Obviously not a bird. The people in the cabin were terrified. They said the engine exploded. And what actually happened is that one of the fan blades had a crack at the bottom, just like I've talked about. And it broke up, and it broke up the containment of the engine. Pieces went flying everywhere. Here's the tragic part. It did break a window, which is unusual, very unusual. A woman was sucked out and subsequently died. But in a way, though, she saved the depressurization, and the plane was able to get down to 10,000 feet, mass drop down. And the Navy pilot is an ex-Navy fighter pilot, female. So she's, of course, just like Sully, she's the ultimate hero. And from an engineering standpoint, though, what's our response? Here it is on the ground. If you look at it closely, it's hard to see in this, but there's actually a missing blade in here. So they knew right away what happened. It was a blade loss. And we know that can create tremendous damage. The idea is to make stronger blades so it doesn't happen. We want to use, we call them super alloys. And then we have these material scientists. They're like the crown jewels of the department. When I was at Pratt Whitney, we actually raided the MIT Department of Material Scientists and brought them on board so they can design stronger metals and ways of making them. The goal is to have a 25,000 hour time between overhaul on your engine. Single crystal blades are what I want to talk about. This was the solution of the blade problem. This is an actual turbine blade. Kind of hard to see from the back, and I'll pass it around. But here's the blade part, and then it's called the fir tree. This is how it hooks into the hub. And if you notice, that looks kind of like, here's a wax mold. This is where the art department comes in. The first time it was made was as a wax mold, and here is the pigtail assembly. And so these are 6 in a row. so what happens, you have this maximal, then you just deposit ceramic on there, and when it's solid, then you can put it into an oven, you melt it, and all the wax comes out. So now these are empty forms. Here's your funnel, you pour in molten metal. And the idea is, okay, now you can solidify that. So you can take that, you can put it right on the desk here, wait several hours, it will solidify. But that's not good. What you want to do is you want to solidify it slowly. So what we do is we put it in the oven, and this is the blade here. So as we draw it down into the cool zone, then the blade, it solidifies from the way up, from the ground up. And the idea is that you want it to be one continuous crystal, not a bunch of snowflake designs all over. You want it to be one crystal. My job was I figured out the heat. We had a thermocouple. I figured out what the heat profile looked like, and then luckily our data points were right on the curve. So I felt very pleased about that. If you just left it on the table, it would look like this. It would be all speckled, and this is called an amorphous solid. It's not periodic, and it's susceptible to, if a bird hits it, it'll probably crack. But if you cool it slowly, the way we do it with our process, it becomes a very smooth, regular periodic lattice, which looks like this. When all your molecules line up, it becomes very, very strong. There is no weak. There's no, like if you've ever worked with wood, if you have a grain, like a knot, you can crack that wood and it'll split right open. So the idea is that these are very strong, and the success rate now is good. 95% of your yield is good and are usable. I've got a small couple slides here. One of my favorite topics. It's very mathematical. Called blade balancing. It turns out this is a fan section. So you've got maybe 26 blades. The key thing is that the blades, they're all individual. You don't make this as one unit. The blades are put in one at a time. You have a hub with 26 slots or 24 slots, and then you lay all your blades out, and then you assemble them one by one. And when you're driving your car, if you have a wheel out of balance, you know what that's like. You hit 40 miles an hour, you feel the vibration. Imagine on an airplane, trying to go to sleep. If you get that vibration, when your head's on the fuselage, you're not going to sleep. So the idea is to balance it. And but the difference is that each blade has a different weight. A lot of these are polished by hand. They have slight bends. They're imperfections. And so you can't just assemble them 1 through 24. So what you do is you have 24 blades, but you actually load a permutation, blade 8, blade 12, and so on. And you try to get the right mix match, or the right match that will be successful. And you have a goal of 1 ounce inch. That was the industry. Okay, with 24 blades, you say, well, we'll just try all the combinations. Guess what? 24 factorial, there are 24 slots with 24 factorial combinations, 6.2 times 10 to the 23rd. And I worked it out. Last year, the Chinese computer was the fastest. I think it would have taken 6 months to do what we do to verify it. Anyway, anybody recognize that number? Any biologists? Yes?
Avogadro's number?
Yeah, I know. Isn't that funny? That's from high school for me. That's Avogadro's number within a very small percent. And it's something going on here. I don't know what it is. I don't think there's any connection. But yeah, good. All right. So what do we do? Here's a schematic. This one has 16 blades. And I said that the weight is actually, you take the weight at the center of gravity of the blade times the distance to the hub. the product of that distance and that weight is called its moment weight. So it's not just the weight of the blade, it's the weight of the blade and how far away it is from the hub. That's called the moment weight, and that's what you have to balance. And you can see here that, here we got two heavy blades, where these CGs are up here, and two light blades. Well, they were paired opposite each other. And so you can do it trial and error, you can do it by balancing. We had a way called simulated annealing, which I won't get into, but it's depending on probability. So you have a pretty good arrangement. Then we said, well, let's take this group and exchange it with that group. And so, let's take this group and let's reverse the order. So we make small perturbations to the order, and if it gets better, then you accept it. If it gets worse, then you roll the dice and say, well, maybe I'll accept it because it might lead to a better solution down the road. So that was our approach. It's designed in theory to get to the global optimum. It's a very slow, circuitous route to get to the answer. It worked, and a year after I left Pratt Whitney, my boss got a patent on this procedure, so we were very happy. One more topic quickly. Geared turbofan is the way of the future for airplanes and plane engines. This is the conventional thing. The fan and the turbine, the compressor and the turbine are all in the same shaft. They all rotate 4,000 RPM. That's bad because this is going so fast that it's breaking the sound barrier. That's why you get a lot of noise. And these are going so slowly that you're not getting efficient burning. So in the last couple of years, companies are saying, let's put a gearbox here. And what that means is you're still in the same shaft, but these components can turn faster than the fan. And so now everybody's happy. The fan's happy, it's not breaking the sound barrier, it's being quiet. And turbines and compressor are happy because guess what? Everything is burning efficiently, and so that's the advantage. Here's what it looks like. This is called a planetary gearbox. This is where the fan is. The fan goes around once when this goes around 3 times. So it's a ratio of 3 to 1. So the fans are 3,000 RPM, and the other components are 9,000. So this is a really significant change in the performance. Here's the engines. These are being introduced into flight now. Huge increases efficiency, reduced noise, pollution. Look at it, 150 million tons of greenhouse gases. It's a cost of Pratt Whitney of $10 billion, but there are some growing pains. Okay, let's go on to, at this point my career is taking off. And I decided that I got an offer to come back to Philadelphia area, and I said I was going to work in space applications with, it was initially Martin Marietta, now it's Lockheed Martin. And here's some of our projects. International Space Station, actually Boeing is the developer for that, but it's huge, it's heavy, 248 miles, it's called a low Earth orbit, so you can actually get to it and service it with the space shuttle. 90 minutes for period. The GPS, everyone is dependent on that now. We have it in our cars, our smartphones, and that you have a constellation of 24 satellites, which are medium Earth orbit. And so the idea is that when you're standing here, 3 satellites can see you at any time, and they can triangulate where you are and get you your position. And there are spares on board, so if one of these goes out, then we can get to it and replace it rather quickly, because this is a national defense security constellation. And look at the weather satellites have done in the last week. All these floods, all these hurricanes, the predictions are on target. Imagine how few people, or how many people could have been killed in Florida without the warning, the early warning. So these sit out over the equator, 22,500 miles. That's called geostationary orbit. And here's another thing, Deep Space Probe, Voyager, already has examined all the outer planets and has now left the solar system. The one thing I can talk about from my career is Landsat, which is a land-based observation satellite. And it's the term we call is remote sensing, because you're actually sensing things on the Earth from an altitude of 438 miles. It's in a polar orbit, and it'll cover the Earth every 16 days. Its resolution is 30 meters, which is pretty big. We have a lot better now. I mean, even the digital globes and the GeoEyes are getting much better resolution. They're limited; they can't get too small, otherwise they're military grade, just like GPS. The key thing is it's a sun synchronous orbit. What that means is that here's the sun, here's the Earth, here's the orbit of Landsat. As the Earth goes around the sun, the orbit of Landsat is always facing the sun. So what that means is that every time Landsat goes around the Earth, it's in the sun. And because you're taking pictures, that's good. If this didn't happen, then sometimes you'd be shooting in the dark. It would be a waste of a mission. So sun synchronous is a very desirable thing. It's always 10 o'clock in the equator when it goes overhead, so everybody knows to look up, smile. Here's some examples. Remote sensing. This is 2016. We had flooding. I can't imagine what these would look like today. Polar ice cap, 1979 to 2007. Again, I can't imagine what the latest edition would be. We have different sensors on Landsat, for different bands, and you can actually look at. We have some that are good for the ocean. You can see silt build up, and you get more new land forming in the delta. Here's the biggest dam in the world, and you can see how it's backed up. It's in China. Spacecraft have attitude. Here's another little insight or a little diversion into mathematics. If you have a satellite, sometimes maybe you're taking a picture straight here. Maybe your next picture is over here, so you have to actually change position or the attitude of the satellite. And so here's a schematic of it. Here's your satellite. It's sitting. This is its rest station, XYZ, three-dimensional coordinates. Leonard Euler said, several hundred years ago that no matter how if you take any object and if you bend it, but if you start here and you end up here, you can always get there with one rotation around one axis. So no matter how complicated your maneuver is, you can always do it in one step, and that's what I've depicted here. The axis of rotation is A, and the angle is theta, and you can see if you rotate around around A, then this box would rotate here. That's how you change the attitude of of a spacecraft, and it's done with gyroscopes and other techniques. So there's the theorem, Euler's theorem. From a math standpoint, if you get to the point where you're looking at linear algebra, it's simply a multiplication by a rotation matrix, which is a unitary matrix. And so if you have your initial position, x, y, z, any point here, multiplied by this matrix, you get the position in your new reference frame. And just to give you, jump ahead, the eigenvalue and eigenvector of this matrix, there's the eigenvector, the axis you rotate about. The eigenvalue tells you how big the angle is. It's a fascinating concept. And if you want to go to another step further of abstraction, you can represent it using a quaternion. And some of you may have heard of that. It's another fascinating. The advantage is this has 9 elements, quaternion only has 4. So that's the most efficient way to rotate a satellite. All right, one of my favorite parts of my time at Lockheed was not, Lockheed, this is already up there when I got there, the Hubble Space Telescope, but they call it the greatest I think it's one of the greatest creations in my lifetime. I mean, it's huge, size of a full bus, school bus, 347 miles, which meant that it could be serviced by the space shuttle. Period is 95 minutes. It's essentially a big camera. There's an 8-foot diameter mirror in here. It's a concave mirror. So the light comes in, is focused, and then it's refracted or back into the camera portion. It's amazing to me. It's been operating for, what, 28 years already. And you have a thermal door here. If you ever get close to the sun, you've got to close the door, otherwise you're going to burn the optics. Solar panels, this is where you get your power. And you have reaction wheels. This is what changes this time you got to move the whole satellite. You can't just move a camera. The camera's immovable. So you have to rotate everything. Here's an application of, I mean, you've all seen, hopefully you've all seen some of the amazing photos that came out of it. This is one of my favorite. Astronomers were looking in the southern, well, lower hemisphere, and there was this patch of sky that looked pretty much empty. You know, only to the naked eye, it was near Ursa Major apparently, but it was, for all intents and purposes, empty. So they said, why don't we take Hubble and we will point it at that point in the sky. Now you can't just take a snapshot because if you have a camera and something's very dim, you have to open the shutter and you have to let that dwell on it for a long time. That's the only way to collect the photons. So with Hubble, we had to do it over 841 orbits. So every time we come around in a favorable location, open the shutter, and Hubble would stare at that location. So build up, build up, build up. These are the images. The white ones are from the visible telescope. Then they said, well, we really need to look. Some of these galaxies that we're looking at are moving fast away. We need to get infrared. That's what that is. And then, so let's put them all together. You have 3,000 images, and here's what we got. This every time I look at this, it's just stunning. That empty spot of sky had 5,500 galaxies. Some formed over 14 billion years ago, almost to the edge of time, and the brightness of a 10 billionth of what the eye can see. So, and you can see some of these are very young and some are more mature, but it's a stunning put down of our ego, because even this vacant spot was teeming. All right, another diversion for math. I thought I'd bring in a little bit of calculus. They said that area of sky, the size of it, take a tennis ball down a football field away, or 110 yards away. That would be the area of the sky that you're looking at. Another way to put it, took an 8-foot long soda straw, looked through it. That's how much sky you see, tiny, tiny. Which gives you an area of 4.9 square inches. That's how big this is. So I said, well, let's figure out how many patches would be in that whole. It's like a mini celestial sphere, because then that'll give us an idea. Well, how many galaxies are there, and how much is in this little thing? So, okay, go back to calculus. Surface area of the sphere is 4 pi r squared. So the radius of this celestial sphere is 110 yards. You get 197 million square inches. So now you got a 5-inch patch here, 197 million. You divide those two numbers, and you can say it would take 40 million patches to cover that celestial sphere. Take that and multiply it times, there are 5,500 galaxies here. So assuming everything is uniform, which we always do in astronomy, multiply that by 40 million, you're going to get 200 billion galaxies. So that's the current Hubble estimate of we are not alone. But the smart guys in Britain, they just said, well, we looked at data, we like it, pretty good, guys, but it doesn't add up. You know, the way that the galaxies are in that picture, we don't think there's enough. You might need dark matter. There's some other things going on. They postulate that it was off by a factor of 10. And there are really 2 trillion galaxies in the universe. So that's what we're working with right now. Again, another put down to me. Every time we're getting more and more insignificant. So, but great, the fact that we can figure all this stuff out. I mean, isn't it stunning? I mean, when I was a kid, the galaxies were called Magellanic Clouds. They weren't even identified as other galaxies. We didn't know about them. So, come a long way. Here's the latest mission launched last year. TESS, Transit Exoplanet Survey Satellite. If you have a distant star and has a planet system, when the planet goes in front of it, it dims the light. So we have now a satellite that looks at those dimmings, and if it does, then it's a possibility of a solar system. It's going to come up 1,500 good candidates, and then they will be studied further with other missions. Something new happened last week. The government wants to get more companies involved. We need to get back to the moon. We need to get to Mars. And so we have $2 billion worth of contracts for Blue Origin, Northrop Grumman, and Boeing and Lockheed. By the way, SpaceX already has a large rocket ready to go, 24 tons to use stationary orbit. The reason this was announced last October 11th, coincidentally, and we said we do, right now, if we want to go to the space station, we got to use a Russian rocket. Ever since our space shuttle was grounded, we have to pay $81 million per ride. And so, and then look at this. On the very same day that this was announced, I don't know if you saw this in the news but Soyuz actually failed to achieve orbit. One of the separations, something happened. The astronauts were lucky this time that they were able to come down by parachute. It's called, euphemistically, it's called ballistic reentry. In other words, you're dropping like a stone. You don't have any way to control as far as I know, and there's no power, and luckily they're okay.
They did land, didn't they?
They did land.
But they didn't go into the ocean. They actually landed on land, didn't they?
That's right. Luckily, they landed on land because Soyuz takes off in Kazakhstan or wherever it is, and yeah, in the ocean, I don't know, that would have been, so luckily it was early enough in the flight that they were still over land. But very scary. Anyway, I think that's enough. Here's a expanded view of Vulcan Centaur, and Aerospace is great, but I'd like to leave some time. 1 or 2 quick questions, if we have any. Yes?
How much do you know about the Webb telescope?
Oh, the James Webb Telescope. That's I don't know if it's up there yet. Is it?
No, it's not.
But it's
coming out.
I think it's being developed. This is supposed to be the successor to the Hubble, and I think it's going to be in infrared or another. It's not necessarily a visible telescope, but it's going to be a phenomenal addition. I mean, luckily the Hubble has optical and infrared, but then the James Webb is going to get. We'll be able to see even farther back in time. Yeah. We didn't get the contract. That's why I don't have to talk about it.
Yes.
Anything else? Yes.
Once TESS tells us about the existence of planetary systems around stars, what is it that they use in order to determine whether it's in the sweet spot where water can exist in liquid form? Is that? Okay. Yeah, the question is with the TESS thing, when you have a transit, when an extra exoplanet goes in front of the star and dims the light, we know that. But then we also have to look at the spectrographic signal that comes from that star and try to decide what the composition is, and if also its distance from the star, whether it's in the Goldilocks zone, not too cold, not too hot. So you've got, but you know, to make everything work like we have on Earth, it's it's a very I mean, you divide by 1,000 every time you add another constraint. Okay. Yes.
So going back to the engine that
Yeah.
you were working on, so you had a compressor that was in there?
Yes. Okay, the question is, in the compressor, in the air-breathing engine, or jet engine, the compressor is successively more and more dense. You get compression ratios of 22 to 1. Your cars are around, what, 12 or 14 to 1? These are 22 to 1. It's very, very compressed air. And at that point, then, you inject jet fuel, and then it explodes. So it's like a car engine on speed. I mean, it's really, that's why they get 100,000 pounds thrust, some of these engines. That's why they're illegal at the, at the Speedway, Indianapolis Speedway. You can't use gas turbines anymore, because they were blowing away the competition. But yes, it's a compression, it's kind of like a car. You compress the air and the fuel, and then it expands.
Guys, I'm sorry to spoil it, but for the sake of time, we need to, if you have questions further, you can ask Tom Pratt. You didn't tell us anything about the extraterrestrial UFOs. I let he knows, but we have him next year. He needs to,
I would tell you, but I'd have to kill you.
I want to present him with a certificate of appreciation. We're really grateful. It was a great talk. I enjoyed it. I think we all learned something. He was kind enough to turn down his honorarium, so we can save some money here. Tom, thank you so much, sir.
Oh, thank you.